So this video addresses the superposition theorem. Superposition applies when there are multiple power sources. They could either be voltage or current sources in the network. And this theorem states that you can solve for the current through a given resistor. Just choose any resistor within the circuit, but you can find the voltage across and the current through that resistor for each individual source, and then you simply add them up together. So the method that you use to determine each of the individual sources is the method that you choose. So you could use you could use mesh analysis, nodal analysis, or the reduce and return technique. So, but to apply this theorem, what you do is you consider just one source at a time. So we're going to short all other voltage sources, and we're going to open all other current sources and solve for the current through the resistor, and then go to the next one, short, so if we're going to do like this voltage source, we're going to short the second voltage source and find the current, and then we'll short this one and put the other one back in. Okay. So before we get started doing that, we're just going to look at a couple of things. Number one, superposition theorem does not work for power, because if you remember, the power through a resistor is I squared. So it's not a linear addition, it's a square term, and so therefore you have to find the current and then the total current using superposition, and then you could find the power of the resistor. But you can't use superposition and find the power of each individual source and then try to find the actual power from just adding them up. So superposition works for voltage or current, but it doesn't work for power because of the square factor in it. Alright, so that's before we actually get started here, I've already got the solution for mesh analysis for both voltage sources. So using both voltage sources here, we find that the current through, let's just kind of say, okay, so this is loop A and loop B. And this is loop B. And of course this will then would be loop C. And so I've applied mesh analysis. I've come up with my resistive matrix and my voltage matrix for both sources. Now I'm considering both sources here. So I've solved these, and I find that the current in loop B, for instance, turned out to be 0.6 amperes. Okay, so it's 0.6 amperes. And so if we look at that, then we see that the current in loop B is this current, and so this just pick this resistor. So I'm going to apply superposition to solve the current through R3. So I'm looking for I3, the current through resistor R3, and that of course is using mesh analysis for the full circuit. That is actually equal to 0.6 amperes. Okay. So now let's take a look at the superposition theorem then. So what we're going to do here is we've got this circuit on the right, and again what we do is we're going to short all voltage sources, and if we had any current sources we would open those other than the one. So we're going to start with the voltage source on the left, and the idea is we want to find the current through the resistor R3. So I'm going to start by just doing the reduce and return approach. So we've shorted out this voltage source. So now we have resistors R4 and R5 are in parallel. So if these are in parallel, right, we have that the equivalent resistance, call it R45, is equal to, using the resistive parallel equation, 1 over 3 and 1 over 1. So if we then solve that, punch that into my handy dandy octave calculator here. So we have resistor R34, or R45 is equal to 1 over 3 plus 1 over 1, and so that gives us this resistor here, R45, and that resistance, that value is 0.75 ohms. And so now we can see that R3 then is in series with this parallel comboed, and so we have a resistor, call it R345, is simply 4.75 ohms. Okay. And remember, when you're doing these calculations, you should take it on out to at least 5 digits so that you prevent any round off. Alright, so now we have this resistor here, R345, which is in parallel with R2. So that gives me a resistor R2 345, which is 1 over 6 plus a 1 over 4.75. So, and then the reciprocal of that. So we'll pop that into octave here. So we have R2 3 4 5 is equal to 1 over 6 plus 1 over 4.75. And remember to double check when you're doing this that this answer here, 2.65, must be smaller than the smallest of those. So remember, we had 4.75, so our answer has to be smaller than 4.75. If it isn't, then there's definitely a mistake somewhere. Alright, so the value of that then, as you can see, and remember, you really want to take this out there to at least 5 digits, so it's 2.6512. Alright, and so finally then, we have then that R1 is in series. So R1 then is in series with that combination. So R total is seen by the 10 volt supply. Okay, E1. R total is seen by the 10 volt supply E1 is equal to, I like to just number these, 1, 2, 3, 4, 5, this resistance, and these last two are in series. So it's 2 plus 2.65, which of course is 4.65. Take it out to the 5 digits so that we prevent any round off. So now we can find the voltage at this node, call it node A, and which is the same voltage as at this node. And so that then would be, using the voltage divider rule, we can find the voltage at node A is equal to E1. And again, this is only due to the left E1 battery supply. Okay, but then that's going to be this resistor R2345 divided by the total resistance, R total, and so that's going to be the 10 volts times the 2.6512 divided by the 4.6512. So that'll give me the voltage at node A. And then if I find the voltage here, which is at node B, I'll have the voltage across the resistor R3, and then I can find the current through resistor R3. So let's calculate this. So we've got 10 times 2.6512 divided by 4.6512, and that gives me 5.7 volts. So VA is 5.7 volts. And that's out to 5 digits, right? So you see that calculation, that's out to 5 digits, 5.7000. So now we can find the voltage drop here by applying voltage divider to just this section here. All right, and so the supply voltage then is the 5.7 volts. So we can do the voltage divider, so we can find VB. Remember, this didn't show up too good. That's supposed to be a B there. So VB is equal to VA times this resistor R45, which was 0.75, divided by the combination, which is 4.75. And so that'll give us the voltage VB. So we had VA was equal to 5.7, and then we get VB then is equal to VA times 0.75 divided by 4.75, which is 0.9. So VB is 0.9. And so we can then find the current through R3. So the current through R3 due to E1 is VA, the voltage VA, minus the voltage VB, divided by the resistance of R3. So that is 5.7 minus 0.9 divided by 4, which is equal to 1.2 amperes. All right, but remember that this current, 1.2 amperes, is flowing from left to right. Okay, so this current is from left to right. All right, so now we're going to solve. We're going to solve by looking at the 5-volt supply. So we're going to short out E1 and only consider E2. And so we have to, using the reduce return approach, right? So using this reduce return approach, we take these two now, which are in parallel. So that's a R1, R2, R1, 2, is going to be a 1 over 2 plus 1 over 6. So R12 is 1 over 2 plus 1 over 6, which is exactly 1.5. So this is R12 here, which is 1.5. Then we take these two, which are in series, which will give me R123, which is 5.5. Now those are in parallel with R4. So we get here this resistor, which is R1, 2, 3, 4, which is the parallel combination of R4 with R1, 2, 3. And so that's a 5.5 in parallel with a 3. So it's a 5.5 in parallel with a 3, which is 1.9412. So this is 1.9142. 94412. All right, and then that, of course, is in series with R5, the 1 ohm. All right, but we really don't have to quite go that far. We can do voltage divider again, so we can find the voltage at this node, and I'm going to call this node D. I mean, it was kind of node B over here, but it's different here because the circuit's actually, because we reduced in the opposite direction, so the circuit's a little bit different. So I'm gonna, I'll I'll call this node D. I guess I forgot node C, but we'll do D, and this will be node D. And so the voltage at node D, so the voltage at node D, voltage divider is E2. So that's E2 times R1234 divided by the total, which is R12345. So that's going to be 5 volts times 1.9412 divided by 2.9412, and that'll give me this voltage. So we get VD is equal to 5 times 1.9412 divided by 2.9412. And that gives us 3.3 volts. So that is 3.3 volts. Okay, and that's out to 5 digits. Alright, so you see there, that's 5 digits. And so that is this point, voltage at point D. And now we can apply a voltage divider again to find this voltage. I'll call this one E. So the voltage at point E is equal to the voltage at point D times the resistor R12 divided by this combined resistance, which was resistance 1, 2, 3. And so that voltage, VE, is equal to the voltage at D times R12 divided by R123, which was 5.5. And that gives us 0.9. So that voltage is 0.9 volts. Okay, now remember, these voltages here are only due to the 5 volt source. It's just a coincidence that that matched the 0.9 volts over here due to the 10 volt. Okay. All right, so we can then find the current through the resistor R3, which is right here, and that is equal to the voltage. Now that is actually going to be going from left to right, and so you can kind of define it either way. Just watch your sign. So if you look at the plus sign here, the plus sign says that when we calculate this, we should use the voltage E value minus the voltage D value divided by the resistance R3. Alright, and so what that's going to give you is a negative, which is telling us that the voltage is going from right to left instead of left to right. And so we have VE, which was only 0.9, minus voltage at D, which was 3.3. So we have 0.9 minus 3.3 divided by the value of R3, which was 4 ohms. Which gives us a minus 0.6 amperes. Okay, so that gives us minus 0.6 amperes. All right, so here we have that voltage, and again the negative sign comes from the fact that this one is going from right to left, and over here we had this one which was 1.2. So we now, using superposition, we can say that the I through the resistor, okay, this was due to the 5-volt source, or E2. Okay, so I R3 total is the voltage I due to I of R3 due to E1 plus the voltage due to I of IR3 due to the second voltage source. But the first one is 1.2 amps left to right, and then the second one, or left to right, and the second one is right to left, so that's where this minus comes in, 0.6 amperes that way. And so of course the answer is 0.6 amperes left to right. So if we go all the way back up and we see, right, that's what we had found before, that the current through R3 is going from left to right, and its magnitude is 0.6 amperes. So this was the application of superposition using the reduce return approach. All right, so it's quite a bit of work using the reduce return approach, and it only actually works for that one resistor. So if you wanted to now find, well, what is the overall current for R2 using the reduce return approach, you've got to kind of, you can still use your calculations through here, but you have to then determine the current through R2 based on each voltage supply. However, if we apply mesh analysis, okay, so if we apply mesh analysis, then all we have to do is, if we take our original mesh analysis and we want to find the voltage just due to this one source here, we just have to come in here in our voltage we just take and look at our voltage vector. The resistance vector doesn't change, so all we have to do is remove the 5 volt. Okay, so we just go in where our 5 volt was and replace it with a 0. That is equivalent to shorting out the voltage source. So we just, here where our 5 volt went, we just put in this 0, and now we can then calculate that. So we just apply our mesh analysis and build our voltage vector with all other voltages and current supplies. Well, you shouldn't have a current supply if you're doing a mesh analysis, but all voltage supplies set to 0. So 10, 0, 0, and I've got the R matrix up here, and so I can then calculate I due to E1. So I due to E1 then becomes R backslash V, right? And I guess I named it VE1. And so you can see, which is what we calculated before, the voltage that was IB, which was through R3, is 1.2. And then we can calculate the voltage. Then we can come over here, and now we're shorting out, right? Now we're shorting out E1. So E1 goes to 0. So the voltage E1 goes to 0. And we stick in E2, which was -5. So we don't, your resistance matrix, when you're doing mesh analysis and superposition, your resistance matrix doesn't even change. So all you have to do is track your voltage supplies. And once you've built up your resistance matrix, and so you have 0, 0, and then a -5 because it was going in the opposite direction. And then we can calculate our, I should have been a 2, I redefined over top of my other one, but we can calculate that current also. So we have that I for resistor 2, or excuse me, resistor 3 it was, is equal to IE1, the second value, IE1, the second value, which was 1.2 right there, minus IE2, and actually you add them, superposition, you add them, right? But because this one is negative, and so you actually are adding, but it's negative because it's going in the opposite direction, so you need to add it. I was thinking subtract, but you need to add, and therefore your overall current is 0.6. So doing mesh analysis, once you got your R matrix built to do superposition, all you have to do is set all the other voltage sources equal to 0. Again, you wouldn't have a current source for mesh analysis. You'd already have to convert all current sources to voltage sources. But set all other voltage sources to 0 and solve for that one voltage source. And then you algebraically, you just add those currents together, right? That's a plus sign there. You add those together. But if they're negative, then you're effectively subtracting them, and you're getting your final result. Okay, so but you don't subtract them, you add them together. All right, so that is superposition. So let's just review. The idea of superposition is if I've got multiple power supplies, I can take one power supply at a time, short all other voltage sources, and if I had current sources, open the current sources, and then find the current due to each individual source and simply add them. Okay, but this only works for the current and effectively the voltage because those are linear. But you have to find the current, and then if you wanted to find the power, you simply use the power law, I squared R, to find the power. You couldn't like find the power in R3 due to E1 and then find the power in R3 due to E2 and try to add those, because those powers would both be positive. You wouldn't have a negative, but in fact E2 is reducing the current in R3, and therefore the power is less. So that's why you can't add. It's for power. You find the currents, and then once you've got the current, you can always find the power. But find the currents using superposition or mesh analysis, whatever technique seems to be best. So again, it doesn't matter when you do superposition, it doesn't matter if you decide to solve it using mesh analysis or the reduce return approach or even nodal analysis.